Okay, we may start with the second part of the lesson. And I would like, before going on, just to rewrite the equation, the last equation that I wrote, not in terms of an integral as a function of k, but exploiting g of e. I would like to rewrite that as an integral as a function of e. So j in this case is minus e. Then we have g of e, that is the density of levels per unit energy. Then we will have f of e, that is the distribution function, the out of equilibrium distribution function. And just to stress the fact that the approach that Sommerfeld used to the effect of the external field over the electrons is somehow always classical. So it goes through the equation of motion, the second law of dynamics. In place of writing h bar k divided by s, that is a quantum mechanical way to write the velocity, I just write v as velocity. So just to stress the fact that the approach is sorry, I just moved the sheet. Yeah, so. And the idea is that in principle, the energy according to the Sommerfeld picture is written in this way, but due to the fact that h bar k is the momentum, this is p squared divided by 2m, and if in place of p we write mv, this is 1/2 mv squared. That is the typical expression for the kinetic energy of a classical system. So in this model, the two ways of writing are exactly equivalent. So if we just define h bar k to be the velocity multiplied by the mass, then the let's say quantum mechanical expression h bar squared k squared divided by 2m is exactly equivalent to the classical one, that is 1/2 mass times square of the velocity. So in this picture, I may use the two expressions exactly in the same way. The problem is again to find f. Just a comment about what I'm going to do. The full topic is related. The topic is related to the Boltzmann's transport equation. That is one equation that you will meet in the next semester within the statistical physics course. So for the moment, I'm not going to do a full introduction. I just want to introduce this topic very briefly, just to make this calculation. So I do not give you the full justification, as that will be given to you in the other course. I just for the moment give a qualitative justification connected to the variation of f that may be observed in this system. So the underlying idea is the same idea that was in the mind of Drude. So the external field brings the system out of equilibrium, but the collisions are the method that try to bring the system back to equilibrium. So the dynamics is similar to the case of Drude. So in that case, external field means out of equilibrium, collisions means going back to equilibrium. In this case, the equivalent of the external field is the out of equilibrium distribution function, and the equivalent of the equilibrium is the equilibrium distribution function. So how does, if we consider f, the actual distribution function of the electrons, how can f change from time to time? So the idea is maybe evaluate how f changes with time. What is the meaning of the distribution function? The distribution function tells us what is the average occupancy of one given level. So if you fix the quantum number that identify one level, then F tells you how many electrons are expected to be in that level. What is the physical mechanism that may affect the number of electrons that you have in one level? That mechanism is represented by collisions. So what is the effect of collisions? The effect of the collisions is to erase any history of the electron and bring back the electron to the equilibrium distribution. So the actual distribution function may change due to the fact that we lose electrons due to the collisions. How many electrons may we lose? If we fix the quantum numbers, the probability that those electrons have to collide, to make a collision in a short amount of time, not df by dt, sorry, I was concentrated on the, just on the variation, sorry for that. If we consider a small amount of time, the probability, as we saw with Drude, to make a collision in that small amount of time is proportional to dt divided by the relaxation time. So the probability to make a collision in a small amount of time dt is dt divided by tau. How many electrons may suffer a collision? If we concentrate in one position, for instance, we fix the energy or we fix K, the number of electrons that we find in that position is proportional to F, because F tells us how many electrons do we have in one specific position or in for one specific quantum number. So the number of electrons that may collide is proportional to F. Due to the fact that after the collision, as the collision erases any past history, those electrons are lost from the point of view of the distribution function because they are set again to the equilibrium configuration. So here we have a minus sign because those are electrons that are lost from the point of view of the distribution function. At the same time, what happens? That other electrons, due to collisions, may appear in the system. So in the same small amount of time, dt, there is the probability that other electrons, due to collisions, appear in the system. And the probability is equal to the probability that those electrons that for the moment we do not know where they are, undergo a collision. So the probability is always dt divided by tau. In this case, the contribution will have a plus sign because new electrons appear thanks to collisions that takes place in other positions. Which kind of distribution function do we use here? In principle, the hypothesis is that after a collision, whatever happened before the collision, the electrons are going back to the equilibrium configuration. In the Drude case, just thermal velocity. In the Sommerfeld model, equilibrium distribution function, so Fermi-Dirac distribution function. So here, to estimate the number of electrons that contribute in positive, we use F0. Just a question. This is the only point where we have, let's say, new physics or new topics. From now on, is just make a calculation, divide, multiply. So from now on, it is just mathematical details. So the question is, the point is, if this equation is fine for you, then everything will be fine, because from now on, just mathematical details. If you have some comments or questions concerning this equation, please let me know so we may discuss. See, I ask to everybody that is connected, do you mind if I repeat in Italian, so maybe I'm able to explain better the topic?
Ok, va bene.
Ok. Allora, l'idea è questa qui, quindi il punto di partenza è simile a quello di Drude, cioè, quindi ho due popolazioni, quella fuori equilibrio per colpa del campo esterno, e quella invece che ha appena subito una collisione, che invece è praticamente ancora all'equilibrio perché non ha avuto tempo di sentire l'effetto del campo esterno. Ora, la variazione di F, che è quella fuori equilibrio, da cosa è dovuta? Ora, immaginiamo di fissare dei numeri quantici, ad esempio il valore di K, così fisso quel volumetto nello spazio e guardo gli elettroni che stanno lì. A quel punto, quelli lì possono subire una collisione e la probabilità che quelli subiscano una collisione dipende da dt su tau. Quanti sono quelli lì? Quelli lì sono in un numero che è proporzionale ad F, perché F mi dice quanto è occupata la zona che sta vicino a K. Quindi il numero di elettroni che perdo è proporzionale al numero di elettroni che ho, che è F, moltiplicato per la probabilità di fare una collisione, che è dt su tau. Quindi il primo pezzo mi dice, se fuori equilibrio ne ho F, la probabilità di perderne alcuni è dt su tau, faccio il prodotto, trovo quelli che perdo, che vanno fuori da quel volumetto per colpa delle collisioni. Adesso però devo tener conto di tutti quelli che, per collisioni che avvengono altrove, compaiono dentro quel volumetto, e questi li conto come elettroni che arrivano. Ora, la probabilità che hanno gli elettroni in altri punti di avere collisioni in quel piccolo lasso di tempo è sempre dt su tau. Il punto di domanda è con che distribuzione li gestisco, cioè qui sapevo di usare la F fuori equilibrio, come gestisco quelli che mi appaiono dopo la collisione. Visto che quelli che appaiono dopo la collisione, che è un mezzo per, diciamo così, cancellare tutti gli effetti dei campi esterni, mi aspetto che appaiano con la distribuzione di equilibrio, allora mi dico, tutti quelli che incamero a seguito di un urto, di una collisione che è avvenuta in un qualche punto del sistema, li descrivo con F0. Quindi mi dico, tutti coloro che hanno appena subito una collisione e sono appena arrivati qua, sono descritti da F con 0. E come ho fatto prima, stimo la frazione di quelli che mi sono arrivati, sempre con la probabilità di subire una collisione in quel piccolo lasso di tempo dt su tau. Quindi diciamo che questo è un bilancio fra quello che perdo a causa delle collisioni nel punto che sto considerando e quello che guadagno a causa del fatto che da qualche parte c'è stata una collisione e io mi trovo degli elettroni nuovi che prima non avevo, e questi elettroni nuovi, che in linea di principio non saprei come descrivere dal punto di vista della distribuzione, li descrivo con la distribuzione di equilibrio perché l'urto cancella ogni pregresso. E quindi il bilancio fra le perdite e le aggiunte lo faccio usando la distribuzione fuori equilibrio per le perdite e la distribuzione all'equilibrio per, diciamo così, i nuovi elettroni che sono arrivati nel sistema. Quindi, diciamo così, facendo questo bilancio, per marcare il fatto che la variazione di F in questo contesto è solo causata dalle collisioni, perché adesso in più e in meno alla fine il meccanismo fisico che produce tutto questo sono le collisioni, spesso come pedice a questo df si scrive collisione. Lo riscrivo meglio qua giù. Metto collisione per marcare il fatto che qualsiasi cosa sta succedendo per colpa delle collisioni. Torna un po' al discorso. Ok, sì.
Ora, lei ha detto, il secondo termine F.0, mettiamo F.0 perché appena stato un urto e quindi mi aspetto che sia proporzionale ad F.0 l'equilibrio. Però il termine con meno, cioè sono quelli persi in seguito a un urto nel nostro progetto. Allora con F', cioè diciamo, è la distribuzione dopo un urto?
No, è la distribuzione prima dell'urto.
Okay.
Cioè nel senso che quelli persi un attimo prima di collidere si comportavano da, chiamiamo, fuori equilibrio. Quelli dall'altra parte, diciamo, il punto più cruciale qui è il secondo, nel senso che il primo uno dice in che stato sono prima dell'equilibrio? Sono fuori equilibrio, perfetto, e quindi li gestisco con l'F per dt su tau. Il problema principale sono quelli dopo l'urto, perché io non so cosa stavano facendo, diciamo, io non so bene la condizione di quelli, in che stato erano, cosa fanno e soprattutto cosa fanno una volta che mi arrivano qua. Quindi l'assunto più forte è l'F0 dt su tau, perché praticamente sto obbligando tutti, che poi è l'ipotesi di base del modello, a comportarsi come se fosse come all'equilibrio dopo la collisione, mentre quindi il secondo è quello un po' più, diciamo così, forzato, se vogliamo. Nel primo invece uno può vederlo semplicemente come F è lo stato adesso che sto per andare a sbattere, diciamo, poco prima di andare a sbattere contro qualcosa, e quindi descrivo quella situazione poco prima di sbattere di collidere con la F. Diciamo, giusto per chiarezza, questo sarà un metodo che tornerà fuori più avanti, quindi fra qualche settimana riprenderemo esattamente lo stesso concetto e lo riproporremo però con qualche dettaglio in più. Quindi a me quello che preme è che adesso veramente in maniera qualitativa più o meno riusciate a incasellare le cose. Ci torneremo su con dettagli maggiori fra qualche settimana, perché con un altro modello useremo lo stesso metodo per cercare di valutare la conduttività, e poi la descrizione formale più completa ci sarà il secondo semestre col corso di fisica statistica. Quindi adesso io non pretendo assolutamente con questi 5 minuti di avervi spiegato l'equazione del trasporto di Boltzmann, perché non è così. Quindi di nuovo adesso, se vi torna a grandi linee, allora diciamo così si può andare avanti, tanto di nuovo da qui in avanti sono solo passaggi abbastanza rapidi. Di nuovo mi basta un'accettazione di tipo qualitativo, perché appunto in 5 minuti non vi ho certo spiegato in maniera formale tutto in modo corretto. In ogni caso, diciamo, al prossimo passaggio ci saranno dettagli in più, informazioni in più, e quindi ne possiamo rintavolare la discussione in quel momento, casomai vi fosse rimasto qualche dubbio o qualche perplessità. Ok? Anche chi è collegato ha qualche domanda, qualche commento da fare, o posso continuare? Okay. Yeah. So if, let's say, using this equation, we may divide by dt, and what we have is that the variation of the out of equilibrium distribution function is minus f minus f0 divided by the relaxation time. So from this equation, you see that the time dependence of the out of equilibrium function is proportional to the deviation from equilibrium, f minus f0, with the minus sign in front. So in general, the idea is that the time variation is opposite to the deviation with respect to the equilibrium. So the time variation tries to bring the distribution function back to the equilibrium. At this point, the idea is to try to express this variation, this time variation, df with respect to dt. What is the meaning of df over dt? This f in principle may depend on all the variables, that is, may depend on the position, may depend on the velocity, and velocity is a synonym of energy. So this is synonym of energy, and may also depend on time. So it may be, maybe due to some external perturbation, we may also observe a time variation of the f function. So in principle, to write down something general, we may write down all the possible dependencies. So at this point, we may expand this variation, taking into consideration the three parameters. So the time dependence may be explicit through t. So we consider that by saying that I make the partial derivative of f with respect to t because I know that there is an explicit time dependence of the distribution function. Then there may be a time dependence not through t directly, but for instance through r, the position, because maybe something changes in the position and that affects the distribution function. And to account for that, I make the gradient of f with respect to the r coordinate, and then I multiply by the derivative of r, that is the velocity. Or there may be a time dependence through the velocity. So maybe the velocity is not constant, but changes with time. And so also the distribution function changes with time. So I make the gradient with respect to v, the velocity of the distribution function, and then I multiply by the derivative of v. So this is just a way to rewrite the df over dt, considering all possible mechanism of t variation of the distribution function. At this point, we apply some hypotheses. The idea is to apply an electric field, constant electric field. So I do not expect an explicit time dependence because the field is constant, does not depend on time. So this is expected to be equal to 0 because I'm not concerned on what happens through the transient between electric field equal to 0, electric field equal to the value I apply, but just at the equilibrium in the let's say when everything is settled and the situation of the system is clear. So I do not expect an explicit dependence on t. I do not also expect an explicit dependence on the position. Since the system is isotropic, the electric field will be uniform over the sample. So I do not expect that there are quantities that may change from point to point or that whose position may depend with time. So also the second term is expected to be equal to 0. In the third case, we have the derivative of v, and the derivative of v is the acceleration, and the acceleration is related to the external field through the second law of dynamics. So this v prime is equal to the acceleration that is equal to f divided by m. So the second law of dynamics enters through the derivative of v. So df over dt due to collisions, in this case, is the gradient of f with respect to the velocity times the acceleration. In this case, the acceleration is due to an electric field. So F is minus E times the electric field. Just to simplify the formalism, I may suppose that the electric field is applied along one specific direction. Let's suppose that is the x direction. So from now on, vectorial quantities will disappear, and I just suppose that E is parallel to EX. So E is equal to x versor times Ex. So from now on, all the scalar products will have just one component, just let's say will include just one contribution, that its contribution due to the scalar product with Ex, because the other two components of the electric field are equal to 0. So at this point, this is equal to the x component of the gradient times Ex. What is the x component of the gradient? F depends on the velocity through the energy, because the velocity, sorry, one comment important. I stop here before making the comment. I just write the full expression, then I make the comment. So at this point, what we have is that minus F minus F0 divided by the relaxation time is equal to the gradient of F with respect to the velocity x component times Ex. Now, on the left side, I have F minus F0. So out of equilibrium distribution minus F equilibrium distribution function. On the right side, I have F out of equilibrium distribution function. At this point, I have a problem, since I have, let's say, I should know the F function to evaluate the gradient, but I have to evaluate the gradient to know the F function. So in general, the approximation that one does is the following. If the deviation of F with respect to F0 is small, I may use on the right side, sorry, on this equation, the value at the equilibrium. So just in case if the deviation of F with respect to the equilibrium distribution function can be considered to be small. So in that case, what is the physical motivation behind that? If we write, I just make the full calculation, so maybe you better appreciate the approximation. In principle, this should be equal to F is equal to F0 plus the deviation from the equilibrium. If I approximate this to it means that I am neglecting the gradient of the difference. So if I know that the difference is small, I expect that the gradient of the difference, or the gradient of the difference is even smaller. Due to that, I may neglect this delta F, this variation in the evaluation of the gradient. Because here you have an equation where you have delta F on the left, F minus F0, and the gradient of delta F to the right. So what you expect is that the gradient of F0 is larger and larger with respect to the gradient of the variation. So you neglect the gradient of the variation. Okay. Yeah. So at the end, we have minus F minus F0 divided by the relaxation time is equal to the gradient of F0 times Ex. F0 depends on the energy, and the energy depends on the velocity. So we may express this by writing the gradient as the derivative of F with respect to the energy times the gradient of the energy with respect to the velocity. So please consider that F depends on V through E. So you have una funzione composta, non mi viene il termine in inglese. So you have that F depends on F depends on V through E. So you make the derivative of F with respect to E, and then the derivative of E with respect to the velocity. Always the X component times Ex. And what is the derivative, the gradient of the energy with respect to the velocity? The energy is 1/2 mvx squared plus 1/2 mvy squared plus 1/2 mvz squared. So if we make the derivative of the energy with respect to velocity x component, we have m times vx. So this is m times vx, because it's the derivative of the first term, because we just need the x component of the gradient. So we just need the derivative of the, sorry, in principle, the gradient of the energy with respect to the velocity has three components, one with respect to Vx, Vy, and Vz. Here, we just need the first component with respect to Vx, so we just need mVx. So this is equal to derivative of f with respect to E times mVx times Ex. Okay, nearly finished. So in this way, we are able to express f as a function of all the other parameters. So using this expression, we may evaluate f. So f is equal to f0 minus derivative of f with respect to the energy times mVx Ex times relaxation time.
Non dovrebbe essere 0.
Sì, sì, chiedo scusa. In DE.
Guarda, 0 meno
In DT?
L'ultima sulla destra.
Sì, no, l'F0 è corretto, però sotto c'è, forse ho scritto male, scrivo meglio l'energia, è una E, ho fatto male io. Ok. Yeah. At this point, we may introduce in the integral that was at the beginning of all the calculation, this expression of f. So the integral was to evaluate the density current was equal to minus E G of V it was minus E G of V F of V, where F is the out of equilibrium function. So in this case, Sorry. I wrote EX, but the acceleration is not EX. My fault. The acceleration is minus EX divided by electronic mass. I hope to be able to correct everything. No, I do not correct, because otherwise, as I moved the sheet, the correction will not be in place. But please, this is minus EX times E divided by M, not EX, because EX is just the field, not the force. And sorry, not the acceleration. So I need the acceleration. I just rewrite the full correct expression. Okay. Yeah. Now, so I include this. So this is now the full expression of the F function. So we have the equilibrium contribution plus the deviation from equilibrium. Please consider that at this point you may split the integral into two parts. One part with F0, the other part with the deviation from equilibrium. The integral with F0 tells you what is the amount of current that flows through the system when the system is at equilibrium. And this contribution is expected to be zero, because at the equilibrium, the average velocity is zero. So I may neglect the first term, F0, as the contribution of F0 is equal to zero to the integral. So at this point, I may just evaluate minus E integral of G of E dF0 over dE Vx times Ex electronic charge relaxation time dE. So I do not consider F0 as the average value due to F0 is equal to zero. And I'm sorry if I miss pieces. Here we are evaluating the velocity. So I was missing the velocity. So I need to include the velocity of the electron. In this case, as the field is along the x direction, I expect that anything happens to the electron is along the x direction. So I just write Vx in the integral. Why do I move the sheet? No, ok, scusate, ho la brutta abitudine, non sto scrivendo sul blocco, quindi ho un foglio, lo muovo. Adesso io vedo bene, ma lì si vede male. Allora, cancello tutto e vi scrivo l'espressione corretta. Ottimo. Perfetto. Now I just write the full final equation. So minus E integral of G of E derivative of F0 with respect to the energy Vx Ex, E relaxation time. Then I have Vx, that is the quantity that I'm going to integrate and to evaluate over the system, and dE. And that should be all. Please let me take the minus sign that is in front of the integral, close to minus c, close to the derivative of f0. So I just write E squared as I have one electronic charge here and one electronic charge here. Then I have G of E minus derivative of f0 with respect to the energy. So I just take the minus sign into the integral close to the derivative. Then I have Vx squared Ex relaxation time dE. As I want to perform the integral as a function of the energy, I should express Vx as a function of E. If I So the connection between energy and components of a velocity is this one here. So in principle, I may write that Vx, if I had just one component of the velocity, I would write energy multiplied by 2 divided by electronic mass. But here I have 3 components, and I expect that on average, the 3 contributions, Vx squared, Y squared, Vz squared, are comparable. So to stress that, I put here 1/3 to say that on average, the X contribution to the energy is nearly equal to the Y contribution and to the Z contribution. So this is equal to E squared Ex relaxation time. The coefficients can be taken out of the integral. So I have 2 divided by 3, 1 divided by the electron mass, and then G of E minus dF su dE, E in dE. Let's have a look at this derivative. In general, let me direct distribution function is 1 below EF, 0 above EF, and different from 0 just very close to EF. Because the range of energies where the function is switching from 1 to 0 is proportional to kT. So if kT is reasonable, and reasonable means low temperature or room temperature, this range of variation is very, very small. Due to that, the derivative of F with respect to the energy is close to what, let's say, is close to a delta, because the derivative is 0 below EF, 0 above EF, different from 0, just very close to EF. Due to the fact that here the derivative of F0 is negative, because F switches from 1 to 0, so you have a decrease of F, the derivative is negative. That's why I took the minus sign within the parentheses. In this way, minus dF with respect to, minus the derivative of F0 with respect to the energy is actually a delta. That is in general a positive function that is 0 everywhere, apart from a value that is different from 0 in one specific position. So in calculating this integral, I assume that minus df 0 over the derivative of F0 with respect to the energy can be approximated with a Dirac delta. So 0 everywhere apart from AF, where we have a value that is different from 0. And that is due to the fact that, again, the Fermi-Dirac function is nearly a step function, even if temperature is different from 0. According to that, we have that the integral is E squared AX 2/3 relaxation time divided by d mass, G evaluated at EF times EF. G evaluated at EF is 3 divided by 2 electron density divided by Fermi energy, and then we have energy divided by Fermi energy, and this ratio is equal to 1. So here, in principle, I should write EF divided by EF to the power of 1/2, but this is just 1. And then I have EF. So this 2, 2, 3, 3 can be simplified. EF and EF can be simplified. And this is equal to E squared relaxation time electron density divided by the electron mass times EX. And this is the density current. This is exactly the expression that we obtained for Drude. And this is mainly due to the fact that in this configuration, we assume that the dynamics of the system, even if the nature of the system is quantum mechanical, the dynamics is classical. So what I wanted to tell you is that even by changing the approach to the description of the electrons, the dynamics of the system will be very close or exactly equal to the dynamics of the Drude approach, because again, the way to handle the interaction with the field is always classical. And one thing that I would like to stress, because that is important, is that from the overall integral over the energy that we had here, so this integral in principle is from 0 to infinity. All energy values contribute to the integral. But due to the fact that the derivative of a Fermi-Dirac function is a delta, or very close to a delta, just the energy close to EF participate to this evaluation, to this calculation. So the effect of having, the fact that the electrons are being described by an equilibrium distribution function that is nearly a step function has as a consequence the fact that in that integral of all the energies that you may use from 0 to infinity, the only energy that participates to the calculation is the only values that participate to the calculation are the energy values close to EF. So this is a consequence of the fact that we have the derivative of a function that is a step function. So it's important to note that in this integral, just what happens at EF is important for the calculation, because here we may neglect all the details that are far away from EF and just concentrate to what happens exactly at the Fermi energy. And yeah, I think I may conclude since it's 11 o'clock. I know that the calculation was a bit long. Maybe I made also some mistakes here and there, so that may make everything maybe not clear at the first step. I just ask you if you may just have a look to what you wrote, just if, let's say, we will use this procedure another time. So we will have the opportunity to review all the steps using a different model. But please just have a look to check if all the things you wrote are fine, if you are fine with the hypothesis, if you're fine with the calculation. If something is not fine, please let me know and we can discuss about that next Monday, or now if you have some questions right now. Also for the guys that are connected, if you have some questions or comments, please. Okay, so if you have not questions or comments, I just close now the connection.